there's an object on the ground, then it is thrown up straight upwards at an initial velocity of 14 meters per second. And eventually the object will stop somewhere. It's going to stop going upwards, and then it's going to start moving downwards. Where it stops moving upwards, that will be the maximum height it reached. And we are asked to find that maximum height. In other words, we want to know the distance from the ground up to where the object stops moving upward. And here we are told that the acceleration due to gravity is 9.8 meters per second squared, and we can ignore air resistance. To solve this, we just use the kinematics equation here. So we won't derive it here. It says that the final velocity, the square of that, equals the square of the initial velocity plus twice the acceleration times the distance traveled during that acceleration. In this case, the acceleration here must be constant. So that's the condition here. You can only use this if the acceleration here is constant throughout the entire journey. So in our problem, the final velocity here is the velocity at the maximum height. And that is 0 because, well, at the maximum height, it now stops moving upwards and it's going to start moving downwards again, right? So that this will be 0. The initial velocity is given to be 14 meters per second. So we're going to put that there later. And acceleration here is going to be the acceleration due to gravity. And this will be downwards because it is opposite the direction of the motion. This will have a negative sign. So A here would be negative G. Okay, so that's negative 9.8 meters per second squared. And finally, we're looking for D here. This is the height that we're looking for. This is the distance traveled from when it started moving upwards. And so we just plug those values in. We get this. And remember, VI here is 14. But before we do that, let's just manipulate this a little bit more. We know VI, we know G, so we can actually move this around so that H is on the other side, and we have on this side VI squared over 2G. And we replace VI with 14 from the given. We have 2 in there, and then G here is 9.8. And notice that this is negative here because we said that the acceleration is opposite the direction of the travel, so that's negative G, and that's why it is negative in here. And now we get this, and what we can do is we do some estimates here. For example, I'm just going to say that 9.8 is 10 because they're close enough, and the choices are not really close to each other, so it's sufficient to just make some rounding off here, and it should be close to the answer. So 9.8 becomes 10, so this will be 14 squared over 20, and 14 squared is actually 7 squared times 2 squared, so that's 7 squared times 4, so there's a 4 there, right? And that cancels with a 20. The 4 cancels with the 20, and so here we have 5, and on top we're left with 7 squared, which is 49. And again, I'm going to make an approximation. It's close to 50, right? 49 is close to 50. And I'm going to do that here. And here I have 5. So 50 divided by 5, that's 10. And 10 is luckily in the choices. So we're good to choose that. We are given this velocity time graph. On the vertical axis is the velocity at any given time, and that time is on the horizontal axis. So if we look at this graph, it just shows us that at the beginning here at time 0, the velocity is also 0, and it just constantly goes up. It's linear, so the velocity goes up at a constant rate until it reaches 28 meters per second. And this happens at 70 seconds after it started moving. And for the next 70 seconds, that's from 70 seconds to 140 seconds, the velocity or the speed remains constant at 28 meters per second. At that point, the velocity starts dropping. So this object starts to decelerate and eventually it stops here. Here, the velocity is 0 meters per second, so it's now at rest. And this happens when the time is 230 seconds after it started moving. The questions that we need to answer are the following. First, what is the acceleration up to this point here? 70 seconds. From 0 to 70, what is the acceleration? We see that that's a straight line, so we know that that's quite constant, right? That's what it means when you see a straight line in the velocity time graph. That means that the acceleration in that segment is actually constant. Second question is, what is the distance traveled up to t equals to 30 seconds? So all throughout, it's been moving. So it was moving from t equals 0 up until t equals to 30. At t equals to 30, it stops moving. So all throughout that motion, how far has it traveled? So let's look at the first one. Acceleration is simply the change in velocity divided by the change in time. And this applies when you have constant acceleration. And that is exactly what we have here. We have a straight line, so the acceleration there is constant. So what we need to do is we just need to get the velocity here and the time here, velocity here and the time here, and we do a subtraction and divide it. So that's the final velocity is 28 minus the initial velocity, which is 0. The final time is 70. The initial time is 0. So you get this, and this simplifies 28 over 70. You can cancel the 7 here. That becomes 4. The 7 here becomes 10. And this is 0.40 meters per second squared. Right. The second one is asking for the distance traveled. Now, if we have a velocity time graph like what we have here, the distance traveled all throughout is just the area under the velocity time graph and above the x-axis. Okay, so that is basically the area that is under this trapezoid here. And this trapezoid, we already know how to get the area of this trapezoid from geometry. And that is simply 1/2 the height of the trapezoid plus the length of this one of the sides, plus the length of the other side. So let me say that again. It's 1/2 the height of a trapezoid times the sum of the length, the shorter length, and the longer length. So that's actually equivalent to just the height times the average of the lengths. Okay, because the average of the lengths is just the sum of the lengths divided by 2. So we're going to use that. So here we have the height is 28, because that goes from 0 to 28. And the length here is just, this is 70, and this is 140. So the length here is 70. And this is 0, this is 230. The length here is 230. So if we plug that in, we get 1/2 height times the sum of the lengths. So that's height is 28, we said that, and 70 plus 230 is just 300. And so we have 14 times 300, which is 4,200 meters. There is an object here, and it's on a frictionless surface. This object weighs, or rather has a mass of 2.0 kilograms. And there are 2 forces acting on it. A force is pulling it to the left, that's 4.0 newtons, and another force is pulling it to the right at 10 newtons. We are told that this object moves horizontally with a constant acceleration. Now we want to find that acceleration. For this problem, we just need to apply Newton's second law. The reason is Newton's second law gives us the relationship between the mass and the acceleration and the total force acting on the object. And what we're looking for is the acceleration, and we have the mass. And now we just need the sum of all the forces. So again, Newton's law is useful here because it tells us the relationship between the mass, the acceleration, and the total force acting on the object. So we know the mass to be 6, and we know the, we know the mass to be 2 kilograms, and A is what we're looking for. Now we just need to find the sum of all the forces, and we can look at the free body diagram here. We only have 2 forces, one pushing it to the left, the other to the right. And so the sum of those forces is 10 minus 4. That's what we got here. 10 minus 4, and that's 6 newtons. Now, this part here is 6 newtons. This part is 2 kilograms. So now we can solve for A. So that's just 6 divided by 2. And so A is 3 meters per second squared. We are given this inclined plane. It is inclined at an angle of theta. And there is an object that accelerates downwards, or rather that moves downwards. And this object will have some mass and some acceleration. Furthermore, we are told that this ramp here is not really frictionless. In fact, the coefficient of kinetic friction is mu prime. Then we are also told that the acceleration due to gravity will be denoted as g. Now we need to find the acceleration of this object. So let's just redraw the diagram with a few more things. So the original diagram don't have these colored arrows, but we drew the colored arrows. The colored arrows indicate the forces that are acting on the object. The first force here is the force of gravity. This is the red arrow moving or pointing downwards. That's with a magnitude of mass times g, mg. Okay, so that's the force that's acting downwards. Now there's another force. We said that the surface is not really frictionless. So there's this force, the friction. That's the green arrow. And finally, we notice that this object is actually kept in place in both the horizontal and the vertical direction. And that means that because if there was only gravity here, then it would be moving downwards, right? So there's some force that balances it, and that's normal force. That's this orange arrow here. That's a normal force. So we're going to take our coordinates to be, the x would be this incline here at an angle theta, and y would be perpendicular to that x. So we choose it that way because that's going to make the computations easier. Now, before we move forward, we just make the note that if this is the angle theta here, and we have a right triangle here, because this arrow for weight is directly or is straight down, right? So it's a right angle here. So this theta here you got 90 minus theta. And so the vertical angle here would have to be 90 minus theta as well. And so the angle here just close to the coordinate, this one is going to be theta. So take some time to convince yourself that in fact this angle here is equal to this angle here, and that's just going to use some geometry. Now we're going to solve for the acceleration of this block. To do that, first, because we decided that we're going to use this direction as our x and this direction as our y, we have to decompose this weight into those directions. So this red arrow will now be 2 red arrows, okay? So this is the x direction of that weight, and this is the y direction of that weight. They have to be perpendicular because the resultant, because we are decomposing the resultant into those 2 perpendicular components, right? That's why they have to be perpendicular as well. Now, we know that this big red arrow is mg, and so this component here, this x component along the x-axis, this should be mg sine of theta, because that's opposite this angle here, right? Opposite over opposite over hypotenuse, that's sine. So this is mg sine of theta, and this one along the y-axis, that component is mg cosine of theta, because that's adjacent to theta, right? Now we are ready to apply Newton's second law, and there are actually two Newton's second law that we can use here, because we have a y direction and an x direction. But in the y direction, you notice that the block is not really moving along the y direction. It's just moving along the x direction, right? Along the direction of the ramp. So we're more interested in this direction, along the x-axis. So we just said that Newton's second law tells us that the sum of all the forces in that direction is equal to the product of the mass times the acceleration in that direction. And that is the acceleration that we're actually interested in, the acceleration in that x direction. So now we just need to know the sum of the forces along the x direction. So we redrew this small arrow here, red arrow in here, just so we can see that clearly, that along the x direction, we have two forces. This component of the weight, which we already said to be mg sine of theta, because it's opposite theta. And the other one here is the friction. And remember, friction is actually the normal force times the coefficient of friction. So the normal force, we said, is this orange thing here. So if you just look at this thing here very quickly, this is a summary of the forces we have here. The red arrow that points downward is the weight. This arrow that points this direction is it's a component of the weight along the x-axis, and we already said that's mg sine theta. And this force here in this direction is the component of the weight along the y-axis, and we already said that is mg cosine theta. Now we said that this is a normal force, and the normal force is just equal to this component of the weight, because you can see that this object is not really moving in that direction, in the direction of y. So that means that the normal force cancels the y component of the weight. And so this normal force is just the weight along the y-axis, and we already know that that is mg cosine theta. Okay, and we said that this friction is actually just the normal force times the coefficient of kinetic friction. We already know the coefficient of kinetic friction, that's mu prime, and we already know the normal force from here, that's mg cosine theta. And so this friction here, we can actually replace that with m prime mg cosine theta, and that's what we have there, right? This one goes here, and this one, we got it from here. And now on the other side, it's just ma, and you notice that all the m's actually cancel, right? We have m here, we have m here, and we have m. And now we're left with just a on this side. And in fact, we can factor out g, because we have g here, we have g here. We have that there. And here we're left with sine theta minus mu prime cosine theta. And this is, in fact, what we're looking for. So we have an object here, block here, and then it is connected to another block here, M2. They're connected by a rope that goes through a pulley in here. This is a simple pulley. And we are told that this table here is frictionless. What will happen is that, of course, if M2 is heavier than M1, then it's going to start moving downwards, right? It's going to pull this M1 with it downwards. And so the rope here will actually be taut, right? And there is tension in the rope because, well, M2 is pulling M1, okay? So if M2 were not pulling M1, if there were no gravity, then there's no tension in the rope. But in this case, M2 is actually moving downwards here, or maybe just balancing M1 exactly so that it doesn't move at all, then but nonetheless, there's going to be that tension T, and we're looking for that tension T. Now, to solve this, we look at the blocks individually. We first look at M1, then we look at M2, and let's look at the relationship between the variables that are involved. So let's look at M1 first. M1 only has one force acting on it in this direction, and that's the tension, right? So for M1, that tension is the total of all the forces. And we said that Newton's second law tells us that the sum of all the forces in that direction is just the product of the mass times the acceleration. And so this is what we have for Newton's second law. We have the tension equals mass 1 times some acceleration. Now, remember that we're looking for tension, but we don't really care about A, okay? And for now, just trust me that in the next steps, we're actually gonna need to get rid of A. So to get rid of A, we have to isolate it on one side. So in this case, we isolate it here, and so A equals T over M sub 1. Now let's look at M2. M2, there's the rope pulling it upwards with a tension T, and there's its weight pulling it downwards. In this case, the weight is M2G, okay? And applying Newton's second law again, the sum of all the forces in that direction is just M2G, assuming that this is moving downwards, M2G minus the tension, right? M2G minus the tension, that is the sum of all the forces. It has to be minus because the tension and the weight are in opposite directions. Now, on the other side, we just have the product of the mass times acceleration. So the mass is M2, M sub 2, and the acceleration is A. Notice that A here should be the same as A here. Why? Because we have one system here. If it's accelerating, however fast it's moving, however fast M1 is moving, that should be how fast M2 is moving as well. So their accelerations must be the same. And now we have these two equations, and unlike what we said earlier, we don't really care about A, but we care about T. So we're going to get rid of A. We already know that A is T over M1, so we can replace this A with that one, okay? And so we rewrite that. This is what we get. M2G minus T, that's this one. M2, that's this one. T over M1, that used to be acceleration, and we replace it with this one. Now, what we're interested in is T, so we just do some algebraic manipulation here, and in fact, what we do here is just we move T to the other side, we factor out T, okay? And when we factor out T, we actually get this one, M2 or M1 plus 1, and you can write it this way. And now we are in a good position to isolate T. So we just multiply both sides by M1 over M2 plus M1. And so this becomes M2G times M1, okay, all over M1 plus M2. So this is the tension in the rope. And you'll notice that this is just like the acceleration due to gravity times some mass. And this is the mass, this is kind of the mass of your system, right? The equivalent mass of your system. That's M1, M2 all over M1 plus M2. We are told that there are two objects here. First object is 4 kilograms. The other object is 1 kilogram. Now the first object is moving to the right, moving towards the second object at 8 meters per second. The second object is at rest. Now they will collide. So this is before the collision. After the collision, we know that the first object, object A, is now moving at 5 meters per second. So originally it was 8 meters per second. Now it collided with B. It's now moving at 5 meters per second. We want to know what is the speed of V, or rather, what is the speed of B after the collision? To solve this, we use the conservation of momentum. The conservation of momentum basically says that the sum of all the momenta right before the collision must be the same as the sum of all the momenta right after the collision. Before the collision, look at the drawing again. Before the collision, the momentum of A is the mass, which is 4 times the speed, which is 8. So 4 times 8, that's 32. That's the momentum of A. The momentum of B is 1 kilogram times 0. So this is just 0. So the sum of those is 32 plus 0. That's just 32. That is the sum of the momenta before the collision. After the collision, the speed of A is now 5, and the mass does not change. So the new momentum of A is 4 times 5, that's 20. The momentum of B is 1 times the speed of B, which is, let's call it V. So this is V. And this is the sum of the momenta after the collision is therefore 20 plus V. And the conservation of momentum tells us that the sum here must be equal to the sum here. So that's 32 in here equals 20 plus V in there. So that's what we write here, right? 32 equals 20 plus V, and that gives us a V of 12 meters per second. There is a spring attached to some object, and the object is 1 kilogram in mass. The spring has no mass. Now, initially, this spring is compressed 20, or rather 0.20 meters from its equilibrium position. If we recall, the equilibrium position is the position of the spring such that it experiences no force, so it will not move. If you put the spring at rest and then you don't put anything there, you don't compress it, you don't stretch it, so that's in equilibrium position. Basically, it's not going to move. It's just going to stay that way. So that's the equilibrium position. Now, if we compress that spring and we get rid of the force that's holding the spring compressed, then the spring is going to bounce back. Okay, so this is what's going on here. We have a spring and then we kind of compress it by 0.20 meters from its equilibrium position. And now we are also told that this spring has a spring constant of 300 newtons per meter. Now the question is, what happens when you let go of the spring? Of course, it's going to bounce back to the equilibrium position, and it's going to do it. It's going to move until it reaches the equilibrium position. The question that we are asked is, when it reaches the position that is 0.10 meters from the equilibrium position, okay, so from 0.20 to 0.10, when it reaches this point, because it's going to move to the equilibrium position, right? It's going to reach this point. When it reaches this point, what is the speed of this object, right? That's the question. And we are also told that the surface here is frictionless. So all the energy is conserved here, and also the spring is massless. So it's not going to take away from the energy that we have. So to solve this, we use the conservation of energy. In fact, the conservation of mechanical energy. It tells us that the sum of the kinetic energy and the potential energy at any point is the same as the sum of those two, kinetic energy and the potential energy at any other point in the motion of the object. So in this case, the sum of the potential energy and the kinetic energy at this point, when it is 0.20 meters away from the equilibrium position, the sum of the potential and kinetic energy there is equal to the sum of the potential energy and the kinetic energy when it's moved to 0.10 meters away from the equilibrium position. And we know the kinetic energy of that object That's 1/2 mass times the square of its speed. And the potential energy is due to the spring. So that's 1/2 K. This is the spring constant times how far it is from the equilibrium position squared. So that's before we let go of the spring. So that's when this x1 is 0.20 meters. Okay, that's x1. X2 would be 0.1 meters. So our x2 here, that this is at that position that is 0.1 meters from the equilibrium position. Again, the kinetic energy is 1/2 times the mass of the block times the v, or the speed of the block at that position. In fact, this is what we're looking for, right? What is the speed at that position? And that's the kinetic energy. The potential energy is again 1/2 times the spring constant times its distance from the equilibrium position, which is, we said, is 0.1 of a meter. And now we notice that 1/2 is actually common to all terms, so we can get rid of that. And so we also replace V1 with 0, because remember that the block started at rest. Okay, so we put it at that position. It's at rest before we let go. So that's 0. And x1, or actually what I did here is just get rid of this one first here. So we're left with x1 squared. And here we have mv squared. Again, v is what we're looking for, and kx2 squared. And I did it this way because I can easily isolate v squared, right? So I move this one to the other side, and I divide the entire thing by m. So first, let's move it to the other side. So when I move this one to the other side, I can actually factor out k. So I factor out k, and I have x1 squared minus x2 squared. That's when I move it to the other side. And now I divide everything by m, so I'm left with v squared here, and here I have m. Now, what I did here is on the top, instead of squaring, I decided to factor this out into x1 minus x2 and x1 plus x2. I just feel that it is easier to compute it this way. Now, I start replacing the variables with their values. K is 300. x1 minus x2, remember that x1 is 0.2 and x2 is 0.1. So x1 minus x2 is just 0.2 minus 0.1, which is 0.1. And their sum is 0.2 plus 0.3, or rather 0.2 plus 0.1, that's 0.3. And the mass is just 1, okay? And this is what I meant. The computation is quite easy, right? The numerator actually reduces to just 9. Okay, so that's 0.1 times 0.3 times 300. That's just 9. And so if you get the square root of that, you get v equals 3 meters per second. And this is the speed of that spring at this position here, when it is 0.1 meters from the equilibrium position. We are told that there is a wave whose frequency is 170 hertz, and the speed of that wave is 340 meters per second. We are looking for the wavelength of the wave. Now, we just recall this relationship between the speed of the wave, the frequency of the wave, and the wavelength of the wave. And this applies to any wave. And we are given the speed and the frequency. So we just rearrange this, and we have here the wavelength equals the speed divided by the frequency, and we're given the speed here to be 340, the frequency to be 170, and we see that the wavelength is just 2 meters. Now, there is an object here that is connected to a spring, and we are told that this object is actually in simple harmonic motion. And in fact, that happens when you compress the spring. So you push this object towards the spring and compress it, and then you let go of that. What happens is that object starts to bounce back to the equilibrium position, but it overshoots, and then it bounces back again, and it does that indefinitely. That's the simple harmonic motion. And you can also do that if you just start at the equilibrium position and then you stretch
the spring, okay? You pull this object away from the spring, then you let go. And again, that object will start to move towards the equilibrium position, but it will overshoot, okay, compressing the spring, and then it's gonna reach some maximum point there, and then it's gonna go back again, okay? So it's gonna do that indefinitely, and that's the simple harmonic motion. Now, in the problem, initially, the system has the following properties. The mass of the object is 4 kilograms, okay? And we already know that when it does the simple harmonic motion, the period of that motion is actually 2 seconds. So let's call it the situation A, the first situation. We are asked, what happens to this period if we actually replace this block with a 16 kilogram block, okay? So this is the question. Let's call the situation B. What is this period, new period? Just to solve this, we just recall that actually we can get the relationship of the period and the spring constant and the mass as follows. So here I use the what I know, which is the angular velocity or angular speed. I denote it with omega. We know that the angular speed is the square root of the ratio of the spring constant to the mass of the object. Okay, so we just know this. But we also know that the angular speed is 2 pi divided by the period of the harmonic motion. We don't really care about the angular speed here, so we can get rid of that. And instead, let's get the relationship of this one here with this one. And so we get rid of the omegas here. We get this relationship. 2 pi over the period equals the square root of the ratio of the spring constant to the mass of the block. From situation B, we're interested in situation B. So we just replace the M here with 16, right? And K, we don't really know the K yet. It's not given in the problem, but later we'll see that we can actually figure that out. So 2 pi over T equals square root of K over square root of 16. Square root of K is still square root of K. So we just flipped it, right? Because we want the T on the top. So T here, so actually this should be an arrow. So I'm just gonna correct that. It should actually be like that, okay? It shouldn't be an equal sign. So now we have T over 2 pi, so we flip that, and square root of 16 is 4, so we have 4 here over the square root of K. Now to get the square root of K, we look at situation A. We were told that it's also in simple harmonic motion, and so this one still applies. So 2 pi over, we are told that the period is 2, and K remains there, so square root of K, and the mass is 4, so we have a square root of 4 here, which is 2. So the 2 here and the 2 here cancel, so we are now in the position to conclude that the square root of K is just 2 pi. And so we can replace this square root of K here with 2 pi, okay? And notice we have a 2 pi here, we have a 2 pi here. So what happens is that they cancel and we are left with T equals 4. So there is an ideal gas with a volume of 1.5 cubic meters and a pressure of 1 times 10 to the 5th pascals. The temperature of this gas is 3 times 10 squared Kelvin. Now, this gas is compressed from 1.5, it is now 1.0 cubic meters. And at the same time, it is heated from 300 Kelvin to 320 Kelvin. The question is, what is the new pressure of the gas after we do the compression and the heating? To solve this, we just use the combined gas law. The combined gas law states that the ratio of the product of pressure and volume to the temperature remains constant. So in this state before the compression and heating, this product must be equal to the product of or rather this term, because it's not just a product, it's a ratio of a product to a number, right? So this term here equals the same term, but this time taking the values after the compression and the heating up, okay? And what we're interested in is P2, okay? So we can actually move the T2 and the V2 to the other side. So we are left with P2 equals P1 here, V1 over V2 times T2 over T1. And we just plug in the values, okay? So P1, we are told, is 1 times 10 to the 5th. V1 is 1.5, V2 is 1. Okay, we have that there. T2 is 3.2 times 10 to the second power, and T1 is 3 times 10 squared, and that's what we have there. And if we do the arithmetic, you're going to see that P2 is actually 1.6 times 10 to the 5th pascals. So there is an ideal gas with a volume of 1.5 cubic meters and a pressure of 1 times 10 to the 5th pascals. The temperature of this gas is 3 times 10 squared Kelvin. Now, this gas is compressed from 1.5, it is now 1.0 cubic meters. And at the same time, it is heated from 300 Kelvin to 320 Kelvin. The question is, what is the new pressure of the gas after we do the compression and the heating? To solve this, we just use the combined gas law. The combined gas law states that the product, the ratio of the product of pressure and volume to the temperature remains constant. So in this state before the compression and heating, this product must be equal to the product of, or rather this term, because it's not just a product, it's a ratio of a product to a number, right? So this term here equals the same term, but this time taking the values after the compression and the heating up, okay? And what we're interested in is P2, okay? So we can actually move the T2 and the V2 to the other side. So we are left with P2 equals P1 here, V1 over V2 times T2 over T1. And we just plug in the values, okay? So P1, we are told, is 1 times 10 to the 5th. V1 is 1.5, V2 is 1. Okay, we have that there. T2 is 3.2 times 10 to the second power, and T1 is 3 times 10 squared, and that's what we have there. And if we do the arithmetic, you're going to see that P2 is actually 1.6 times 10 to the 5th pascals. We are given a monoatomic ideal gas, and the volume of this gas is 5 times 10 to the minus 3 cubic meters, and the pressure is initially 6 times 10 to the 4th pascals. This pressure is increased while keeping the volume constant. So the final pressure is 10 to the 5th of a pascal, and the volume is still the same. The question is, what is the change in internal energy? The change in internal energy of a substance can be computed using the first law of thermodynamics, which states explicitly that the change in internal energy equals the amount of heat added to the system minus the work done by the system. And so what we're interested in here is this expression, this value, the change in internal energy. Do we know the work done? We know that the work done is 0. Why? Because the volume remained constant. There was no work done. Work is basically the amount of compression or expansion. So there's no compression, no expansion here. The volume is kept constant. We say it's isochoric. So the work here is 0. Now we are left with this Q here. That means that what we're looking for is actually just Q. That's how much heat was actually added to the system. And we can compute this from the given. The given is, here we have the volume and the pressure. Here we have the volume and the pressure. So we actually can compute this if we had the temperatures, right? Because we know that Q from calorimetry is actually the number of moles times the heat capacity times the change in temperature. But since we don't have the temperatures, we will compute them from the given, the pressures and the volume. And since we have two temperatures that we need here, we're going to use the ideal gas law. Okay, that says PV equals nRT. So for the first temperature here, that's going to be P1 V1 over nR. And the same for the second temperature here. We're just going to change the subscripts. Now notice that V in both cases for V1 and V2, they're actually the same. So we don't really need the subscripts because they're the same. R here is the universal gas constant, and the gas constant is a constant, so we don't need that. And N here, it doesn't really change throughout the processes, right? So this is also constant. So actually the subscripts would only apply for P, right? And also, so here again, N is the number of moles of the gas. And here we have the heat capacity at constant volume. So that's important because we know that the process here happened in constant volume. The volume didn't change. And we have a different C for when the volume changes, but the pressure is kept constant. In this problem, specific problem, we know that we have to use this value for constant volume. And we know that that value is actually for monoatomic ideal gases. It's 3/2 of R, this R here, okay? We know this for monoatomic ideal gases. While for other kinds of gases, this will be different. But for monoatomic ideal gases, the heat capacity at constant volume is 3/2 of the gas constant. Now we have everything we need. We have the value of this in terms of R, and we have the values of T2 and T1 in terms of PV and N and R. So we can now substitute these. So the change in internal energy, we said, is just Q, and Q is just this. So we replace the values. The N here, still N here. The CV here, heat capacity, is this one, 3/2 R. T2 is, okay, T2 here should have been P2. Yeah, it should have been P2V over NR, and this should be P1. Okay, so this is mistaken. It should be P2 and it should be P1. But the V and the N and the R here, they're constants. So we can just, in fact, we can cancel the N and the R in the denominator with these ones here, and we can factor out the V. And here is what we've got. We got 3/2 times V. Now here is correct, P2 minus P1. Now, the volume is given to be 5 times 10 to the minus 3. Pressure is given to be 10 to the 5th minus 6 times 10 to the 4th. So I just factor out the exponent 10 to the 4th. So here we have 10 minus 6. And notice that 10 to the minus 3, 10 to the 4th, they cancel to be just 10. 10 minus 6 is just 4. 5 in here, we have 3/2. Then you multiply them out together, you get 300 joules. This is the change in internal energy, which is also the amount of heat added to the system.
We have a monoatomic ideal gas. The volume is 2 times 10 to the minus 3 cubic meters. The pressure of the gas is 2.2 times 10 to the 5th pascals. Now, the gas is allowed to expand, and the pressure reduces to 1 times 10 to the 5th pascals. During this process, the temperature is kept constant. And overall, after the entire process, a total of 3.5 times 10 squared joules of energy was added to the system. We are now asked how much was the work done by the system. To solve this, we look at the first law of thermodynamics, which says that the total change in internal energy is equal to the amount of energy added to the system, that's the heat, minus the work done by the system. In this case, we are told that the temperature is kept constant. This was an isothermal expansion. And so the change in internal energy is zero. There is no change in internal energy because internal energy depends only on temperature and the amount of gas in the system. Obviously, there is no change in the amount of gas in the system. That is safe to assume. And we are also told explicitly that the temperature was kept constant, and therefore these two things were kept constant. And so internal energy is also constant. And so the change here is zero. And what we're left here is 0 equals Q minus W. We're looking for W. And if we rearrange this, we see that W equals Q, but we're already given Q. And that's 3.5 times 10 squared joules. And so this is the amount of work. This is also the amount of work that was done by the system. We have this circuit shown. We have two voltage sources, 2 volts and 7 volts, and we have 3 resistors, 2 ohms, 4 ohms, and 6 ohms. And the problem asks us to find the current through this resistor. And for convenience, we will call the current through this resistor I1 plus I2, where I1 is the current through the first resistor here, I2 is the current through this resistor, and they are in this direction to the left. And so I1 goes here, I2 goes here, and so they merge at this node, and they go through R3, and therefore that sum is I1 plus I2. And what we're looking for is this sum. To solve this, we need to find this sum, and we will use Kirchhoff's voltage law. It basically says that if you choose any loop in the circuit, the sum of all the voltages across the elements in that loop will have to be 0. Okay, so we're going to choose the following loops. We're going to choose this loop, the outer loop that goes through R1 and R3, and the other loop is the one that goes through R2 and then R3. So for the first loop, we have 2 volts here. So that's 2 volts minus whatever the voltage drop here is. So the voltage drop is R1 times I1, right? From Ohm's law, that's resistance times the current. That's the voltage drop. So I1 times R1 minus, so we have this loop here, outer loop. So the other resistor is this one. So minus I1 plus I2, that's the current, times R3. So that's the voltage drop across this resistor. And so we get this first equation here. The second equation is obtained from the second loop. So remember, the second loop that we chose is this one here. Okay, it goes through this power source, voltage source. So you get 7 volts minus the voltage drop across R2, which is I2 times R2, minus the voltage drop across R3, which is I1 plus I2 times R3, which is 6 ohms. And that should be 0. Again, we write it here. Now, what we're interested in is I1 plus I2. So what we're going to do is we're going to solve for I1 and I2, and then we add them together. Now, the way we do this in math is just, well, let's first combine like terms, and then we eliminate the variables. So first, in the first equation, we're going to replace R1 and R3 and R2 here with their values. So R1 is given to be, let's look at that. R1 is 2, R2 is 4, and R3 is 6. So R1 here is 2.
R3 here is 6. And so we have I1. We also have I1 here. We can combine the 2 and the 6. So actually, before we do that, let's just replace the R's first. So here we have, and then we move the 2 to the other side. So in fact, what we're going to do is we're going to move these negative values, negative I1 R1 minus I1 plus I2 R3 to the other side. And so we're going to get 2. We're going to have 2 here, and this one becomes positive on the other side, and this one becomes positive on the other side. So we're going to be left with 2 equals R1 times I1. Okay, I1 times R1. So this is R1, which is 2, plus I1 plus I2 times R3. That's what we have here. And R3 is, well, 6. So that's what we have here. And now we do the same thing for the second equation. So 7 is left here. I2, R2, move to the other side. This is R2, which is 4. This is I2. And then R3 term to the other side, we get 6 I1 plus I2. Now, we combine in this first equation, we combine the two I1s. So we got 2 plus 6, you got 8 I1. And I2 is just 6 I2. Second equation, we combine, well, we have I1 here times 6, so 6 I1. And we have 4 I2 plus 6 I2, we get 10 I2 in here. Okay, so we now have two equations, and we can get rid of either I1 or I2. So what we're going to do is we're going to get rid of I1 first. So we have to multiply the first equation here by 3/4. If you multiply the first equation by 3/4, this is what you're going to get. On the left side, you're going to get 3/2, right? Because 2 times 3/4 is 3/2. Now, we have 8 times 3/4. That's going to be 6 I1. 6 times 3/4, that's 9/2. Okay. And now you can see and then we just copy the second equation here. 7 equals 6 I1 plus 10 I2. You'll notice that we can eliminate the I1s here. So we just subtract, right? 7 minus 3/2, we get 11/2, right? 7 minus 3/2, we get 11/2. 6 minus 6, that's 0, so it's gone. 10 minus 9/2, that's actually also 11/2. Okay. And what we have here is now, because that's, so the way we get it is just 10 times 2 over 2. So 20 over 2. 20 over 2 divided by 9, or sorry, minus 9 over 2. That's 11 over 2. And so you notice on this side is 11/2. On this side is also 11/2. And therefore, I2 is actually just 1 ampere. Now we have this I2. So we can substitute this I2 in here, okay? So we replace this I2 here with 1, and we can now solve for I1. And so we copy this entire thing. 3/2 equals 6 I1 plus 9/2 times 1, okay? So we get this equation, and we just move the 9/2 to the other side and divide the entire thing with 6 by 6, and we get I1 equals negative 0.50 amperes. And now what we're looking for is I1 plus I2. So we add them together. I1 plus I2 is minus 0.5 plus 1. That's a total of 0.5 amperes. And this is the current through R3 in here. We are given this circuit. We have 4 resistors arranged in this manner, and they have common nodes here. We call that node C, and here node D, and here at node A and node B, there's a galvanometer between them. Now the galvanometers actually just measure current, right? And so we are also told in the problem that the galvanometer here doesn't move, and so it measures 0 current. When you have 0 current, that means that the voltage between this node A and B the voltages are the same. That's why no current can flow, because the voltages are the same, right? And Ohm's law says that if you have a voltage difference, then the current is proportional to that voltage difference. And what we have there is we have 0 current, so that means the voltage difference is also 0. So we now know that A and B are on the same voltage. Now C and D, so there's a power source here. Now, what we know is that because C is common to both branches, and as well as D, and the voltage in A and B are the same, we can actually say that the resistors, this R here, with respect to this other resistor here, that ratio is actually the same as a ratio here, 7 to 10, because that's the only way you can have the voltages here will be the same, right? That's when you have exactly the same proportion, because the voltage drop is proportional to the resistance, right? And so the resistances should have the same proportion for the voltage drops to be the same. And if we write those in math terms, we say that the ratio R is to 8 is the same or equal to 7 is to 10. And that's what we do here, right? R is to 8, 7 is to 10. And now we just have to solve for R. So this is just 7 over 10 times 8. That's R. And if you solve that, that's going to be 5.6 ohms. In this problem, we are asked for the total capacitance of the circuit. Okay, what we have here are 3 capacitors, and they are in parallel. So the first 2 are in series, 4 and 6, and that combination is in parallel with 3. And we want to know the capacitance across A and B. So the way we do this is we just combine it according to the series and parallel rules for combination of capacitors. When capacitors are in series, we use the parallel law, right? Well, I call it parallel law, but it's basically combining them in the manner that we combine resistors in parallel. That means to get the equivalent resistance of these two, or equivalent capacitance of these two capacitors, is you multiply them 4 times 6 divided by the sum. 4 times 6 divided by 4 plus 6. That's the equivalent resistance here. And now you can reduce that into just one capacitor. Now you have 2 capacitors in parallel, this combination and this. And the way you combine parallel capacitors is you just add them. So whatever the combined capacitance of these two plus 3, that's going to be our new capacitance. Okay, so we already did the combination of these series capacitors. That's 4 times 6 over 4 plus 6, so that's 24 divided by 10. And this one we add plus 3. So 24 divided by 10 is 2.4 plus 3, you get 5.4 farads for the equivalent capacitance.
The setup has 2 charges, QA and QB, and they are of equal magnitude, but QA is positive and QB is negative. They are of the same distance from the center. So this is QA, and here is the center that's 4 meters away, and QB is also 4 meters away from the center. Along the center line, there is the point P, and P is just 3 meters above the center, or the midpoint of QA and QB. And there's another point here, Q, and Q is just closer to QA than to QB. More precisely, it is situated 3 meters away from QA, but 5 meters away from QB. But it's on the same line as QA and QB. We're also told that for this problem, we will consider K, which is the constant in Coulomb's law, to be 9 times 10 to the 9th Newton meter squared per Coulomb squared. Now, what we're interested in is, first, what is the direction of the electric field here at P? Okay, remember P is right at the middle of QA and QB, except that it's 3 meters above that middle. And we also want to find the magnitude of that electric field here at P. And the third problem is we want to find the magnitude of the electric potential here at Q. So let's look at the first problem, the direction and the magnitude at P. So the direction of the electric field. The electric field points away from the positive charge and towards the negative charge. Okay, so here, if we draw the electric field due to QA, what we're going to find is that it's going in all directions, right? Away from QA. So here at P, let me just draw that. So here, what's going to happen is that you have from here, it's going to be pointing that direction, right? It's away from
away from A, right? So it's actually around all directions, yeah. But if we are just going to look at the point P, it's going to look like this, right? And for QB, everything is going to be pointing towards QB. So it's going to look like this, right? So from all directions, there's going to be lines pointing to QB. And these are all electric field lines. Now the question is, what is the total direction here at P? Well, we notice that due to A, there's this electric field. Due to B, there's this electric field. And because A and B, QA and QB, are the same distance from P, the vertical components of these electric fields are actually the same. The vertical component of the electric field due to A is pointing upwards. The vertical component of the electric field due to B, QB, is pointing downwards. But because, again, the charges are the same distance to P, then these vertical components are actually of the same magnitude, but their directions are different, and so they cancel, okay? So now we know that the electric field at P do not have a vertical component because they cancel, right? However, as for the horizontal component, notice that due to A, it still has a horizontal component pointing this direction, right? Because the arrow is moving, is pointing this way. And due to QB, it still has this horizontal component, right? Because again, the arrow is pointing towards QB like that. And so we can safely say that in fact, the resultant electric field is actually pointing this direction to the right, right? In fact, it's double the component due to A, right? And so that's what we have here, right? I'm just gonna, I drew it here again, right? So you have this, the red one pointing upwards, that's due to QA, and this red one pointing downwards, it's due to QB, and the vertical components are the same, albeit in opposite directions, and so they cancel, and so the remaining direction is just moving this direction, right? And that's twice this component here, right? They add up, okay? Because they have the same. And so that is our answer for the first one. The direction is towards the right. And now, okay, so in fact, we're going to draw that, right? So this plus this, okay, the vertical components cancel, the horizontal component that remains, components that remain are this, and so that's a longer arrow, right? And for the magnitude of that, then we just need to find this, we just need to find one of them, right? And we double that, this one, because they're of the same length, right? They're the same distance from this point P. So let's just look at this component. Notice that this component is in fact just the component of this one, this red arrow. But the red arrow, we can get that from the definition of electric field, and that's K, that was the constant that was mentioned earlier, 9 times 10 to the 9th, times the charge, okay? So QA, you get the absolute value of that, you divide it by the square of the distance from QA to that point, okay? So that distance, we already know that this vertical distance is 3, horizontal distance is 4, okay? That's from the center from P, right? And this is a right triangle, so there's 4, 3, therefore this distance here is 5, right? 4 squared plus 3 squared, you get a square root of that. It's from the Pythagorean theorem, and that's 5. The distance here is 5 from Q to P. And so we get 5 squared here. However, we only need the horizontal component, right? We don't need the resultant because we said that the vertical components already cancel. And so we have to get the cosine of that angle, right? The cosine of this angle here. But we also know the cosine of that angle because that is just, we know that this is 5 here. And so the cosine is just the opposite, the adjacent side, which is 4, divided by the hypotenuse. So that's 4/5. And so we replace all the values. K is 9 times 10 to the 9th. QA is 2.5 times 10 to the minus 9th. And we already computed D, which is 5. And here cosine theta is just 4/5. So
We replace that and we do the computation. You're going to get 1.44 Newton per meter, right? Is it Newton per meter? Hold up. That's force per, so that's force per charge. So that's Newton per Coulomb, right? Okay, now, so we now look at the third problem. Third problem, so let's redraw it here. This is Q here. Q is closer to A than to B. But what we're looking for is the total electric potential. Now, to do that, you just sum the electric potential due to QA and the electric potential due to QB. And electric potential is just K, that's the constant earlier, times the charge causing it, divided by the distance. So it's KQA over DA. So this is that distance, which is 3 meters, that's DA, plus K times QB divided by DB, and that is this distance, which is 5 meters. Okay, so you just add that, and you notice that K can be factored out. That's 9 times 10 to the 9th, and inside QA is 2.5 times 10 to the minus 9. QB is minus 2.5 times 10 to the minus 9. The distance dA from QA to Q is 3. From Q to QB is 5. Okay, and then we do the arithmetic there, and you're going to get just 3 volts. And yeah, this is the total electric potential due to QA and QB at point Q.